Welcome to calculus. You will master complex problems, but forget how to add. On this episode, Stevenson will demonstrate limits involving infinity. We know that the symbol of infinity, or for infinity, doesn't actually represent a real number. But what in fact we use infinity for is it describes the behavior of a function when the values in its domain or range outgrow all finite bounds. Now, we did talk a little bit about infinity in the last video, briefly, but for the most part, we have talked about infinity back in IM3. So let's review something that we worked with extensively in IM3, which is the reciprocal function, 1 over x. So this is what it looks like right here. And as you recall, we would describe its end behavior as follows. We would say as x approaches positive infinity, so that means as we start at 0 and we go to the positive side of the x-axis, we would see that the function 1 over x, or we would say the y values, is approaching 0. In calculus, this is how we would write it. We would say the limit as x approaches positive infinity of 1 over x equals 0. Or the limit of 1 over x as x approaches positive infinity is 0. Now, what if we look at the left side end behavior? As x approaches negative infinity, 1 over x approaches 0. It's just from below. The limit of 1 over x as x approaches negative infinity is also 0. So we would say that the line y equals 0 is a horizontal asymptote of this graph. So we've actually done this before in IM3. So what we're doing is we're upgrading it using limit notation. So what we've actually done here by using limits with infinity is we're actually in fact defining the horizontal asymptote of a graph. So when you think about it, when you're finding horizontal asymptotes, you're essentially doing limits of your function as x is approaching a positive or a negative infinity. But that doesn't mean every time you do this, it's automatically a horizontal asymptote, okay? So it becomes a horizontal asymptote if either the limit of your function f of x as x approaches positive infinity goes to some number, or the limit of f of x as x approaches negative infinity goes to some number. So in other words, if you take the limit of your function as x approaches either positive or negative infinity, if it ends up being a number, then by definition, that is a horizontal, a horizontal asymptote. So this idea of horizontal asymptotes can be used in combination with the squeeze theorem. Now, I didn't touch on the squeeze theorem last lesson. I'm going to touch on it here. So let's look at example 2. So it says find the limit of f of x as x approaches positive infinity if f of x is sine of x over x. Okay, so essentially what we're being asked to do here is to use the graph and the table and the figures. Okay, and we can suggest based on the graph and the figures here that as x approaches positive infinity to the right, as x approaches positive infinity, the function itself is going to 0. We can tell by that, and we can also tell by the table of values it is going towards 0. But we can actually use something called the squeeze theorem. Essentially what the squeeze theorem says is that if you can show that the particular function you're looking at, if it's bound between two outside functions and the limits of the two outside functions are exactly the same, then it follows the limit of the function that's between them must also then have the same limit. Why? Because the function is essentially squeezed in between the other two. Okay, so look at the following example here. So going back to example 2 now. So we know we can start with sine of x. Sine of x we know is bound between -1 and 1. That's our sine function, our sine wave. The range is -1 to 1. And since x is going to be greater than 0, because I'm doing all the x values approaching positive infinity, what I can do now with this inequality is I can divide by x all the way through on all sides of here, because I don't risk dividing by 0. So this algebraic step is sound. Now you may be wondering, why am I doing that? Well, I'm trying to make sine of x over x. So I start with something I know, and I modify it, okay, doing everything to all sides based on this value, or this restriction here. Now what I can do is I can take the limit of all three of these. Now, the limit of 1 over x we already know over here. as x approaches positive infinity, we know 1 over x is 0. Now, negative 1 over x, if you don't remember, negative 1 over x looks like this. So if I take the limit as x approaches positive infinity of this function, I can see it's still going also to 0. So essentially, the limit of this function is 0. The limit of this function is also 0. So if the outside limits sine of x is bound between, if those limits are 0, therefore the limit of sine of x over x as x approaches positive infinity must also then be 0 by the squeeze theorem. Okay, and because this function is even, remember symmetry-wise, then it would follow that if we were to do the limit on the other side as x approaches negative infinity, it would also in fact be 0. Okay, now there are some additional properties that also apply to limits with infinity, and you have the limits from the first one, but then it also applies here. So what I wanted to, now what's really cool about this is I can actually break this up. Okay, so check this out. So I can rewrite 1 minus cosine of x divided by x squared as 1 over x squared minus cosine x over x squared, right? Because now I have two fractions where the denominators are the same, therefore I can break them apart. Now this may be weird because normally we have fractions with common denominators, we want to bring them together, right? So I want you to go in reverse order and break them apart. Now you may be wondering, why would I want to do that? Well, remember those limit properties? This now becomes the limit of a difference, which means I can do the limits individually. So let's do the limits together here. So let's do this limit first. So this is the limit as x approaches positive infinity, 1 over x squared. Now, in my textbook, this question number 9, the question number itself actually has like a gray box, which means it's like filled in. What that means is you're not supposed to use any technology to do the problem. But in this particular case, we don't have to. 1 over x squared, we studied this last year. What's the limit as x approaches positive infinity? Based on our graph, we can see this is 0. Now this is not as easier to sketch, but we can use the squeeze theorem to find this. So again, let's start with what we know. We know the cosine of x is bounded between negative 1 and 1, because that's the range of it. Okay. Now I want cosine of x over x squared. So what I want to do is I want to divide this by x squared on both sides. Now, it is safe to do so. How do I know that? Well, x is going to be greater than 0. How do I know that? Because my limit's going to positive infinity, so I'm putting x values in that are always going to be positive. I won't have 0 in here, so I can divide this number through. Now, we're going to apply the limit on all three of these. Negative 1 over x squared is just a reflection of this graph over here. So let's put it right there. So what's the limit as x approaches positive infinity of negative 1 over x squared? Well, we can see it's going to be 0. This is the limit we're trying to find. And the limit of 1 over x squared is this one, which we can see is 0. So, as you can see, this limit is bounded between these two. So we would say, therefore, the limit as x approaches positive infinity of cosine of x over x squared equals 0 by the squeeze theorem. This means this limit right here is 0. So this is 0 minus 0. Therefore, the whole answer is just 0, this limit right here. Okay, so this is what I just did, as I basically applied my understanding of behavior of functions. I used the squeeze theorem over here, and then I used properties to break this up, and I did the limits individually.